talking about oblique asymptotes and looking at some special cases of the reciprocal functions we've been looking at. We've built up now to the point where we're starting to talk about functions that aren't necessarily linear functions over linear functions. We could have different degrees in the numerator and the denominator. In the last video that you watched, I did mention that there's going to be three different cases that we look at. The first one is if the degree on top is less than the degree on the bottom, then the x-axis is the horizontal asymptote. An example of that would be the functions we started looking at, those reciprocals of linear functions. So 1 over 2x minus 3. This would have a horizontal asymptote that is the x-axis. The video that you watched over the weekend, we were looking at functions where the degree on top is equal to the degree on the bottom. And then we're going to see that the horizontal asymptote is the line y equals a over b, where a and b are the coefficients of the highest degree terms. A more complicated example of this could be the function 3x squared minus 1 over 2x squared. And here we would have a horizontal asymptote at the line y equals 3 halves. And now today we're going to start looking at situations where the degree on top is higher than the degree on the bottom. And then we're going to see that there's no horizontal asymptote, but we may see a slant or a diagonal or an oblique asymptote. And we want to see how we can go about finding those asymptotes today. Just to reiterate, when the degree of the numerator is 1 more than the degree of the denominator, an oblique asymptote may be formed. So our investigation today is going to involve graphing this function, 2x squared plus 3x minus 1 all over x plus 1. And we're going to do this like we did in class, so we're going to have some steps to follow. We'd like to factor if we can, so we'll factor the numerator and the denominator if we can. We'd like to identify our asymptotes. We'd like to identify our intercepts. We may need to investigate behavior around some of these different points. And once we've done that, we should be able to draw a pretty good sketch of this function. So starting with factoring, let's see if we can factor this. We're looking for two numbers that multiply to -2 and add to +3. And I can't think of two numbers off the top of my head, so I don't think that can be factored. So for now, we'll leave this as is. So this does not factor, at least not easily. We'll come back to that. Next, we're going to spend time identifying any asymptotes. So we'll proceed as normal with this. We know that there's a vertical asymptote whenever the denominator equals 0. We know we have a vertical asymptote at x equals -1. Last week when we were trying to find horizontal asymptotes, we would check values of x that got very, very big. So as x approached positive and negative infinity. And we can do the same thing here. We can evaluate our function at 100. We can evaluate it at 1,000. We can evaluate it at evaluate it at 10,000. And we can see what we get. We can see if our function is approaching something. And we can do the same thing for values that are approaching negative infinity. So we can test negative 100, negative 1,000, negative 10,000. So why don't you try that on your own? So once I've plugged in these very, very positive numbers and these very, very negative numbers, I notice something. I notice that my values keep getting more positive and more negative. So I can summarize this as x approaches positive infinity, f of x is also approaching positive infinity. And as x approaches negative infinity, f of x is also approaching negative infinity. So we haven't really learned anything from this except the fact that there is no horizontal asymptote. It's not approaching anything. But let's go a little bit further with this. Let's look at this function, 2x squared plus 3x minus 1 all over x plus 1. This looks like the work we were doing in Unit 2 when we were being asked to divide. So let's actually do the polynomial division. Let's divide that quadratic by that linear function and see what we get. So I'm dividing by x plus 1. Using synthetic division, so I'm going to fill in my chart. Bring down the 2. 2 times 1 is 2. 3 take away 2 is 1. So what I see when I divide 2x squared plus 3x minus 1 by x plus 1 is the linear function 2x plus 1 minus a remainder of 2 over x plus 1. And this is going to help us graph the function. What we're looking at is the equation of the oblique asymptote. So by taking this function where the degree on top is higher, 1 higher than the degree on the bottom, and actually doing the division, we were able to find our oblique asymptote. So we have an oblique asymptote at the equation y equals 2x plus 1. Next up, we'll identify our intercepts. So y-intercepts happen when we sub 0 in for x. So we have 2 times 0 squared plus 3 times 0 minus 1 all over 0 plus 1 which gives us a y-intercept at negative 1. for the x-intercepts, we need to solve this equation when the y value when the function is equal to 0. So as always, we'll start by cross-multiplying. Which gets rid of the denominator. And now I have this quadratic that's equal to 0. And in grade 10 and grade 11, when you saw something like this, a quadratic equal to 0, you would have factored to try and find the x-intercepts. At the beginning of this question, we realized we couldn't factor. So there is still something that we can do to find the x-intercepts. We can use the quadratic formula. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And we can plug these values in for a, b, and c. So we get negative 3 plus or minus the square root of 3 squared minus 4 times 2 times negative 1 all over 2 times 2. We're evaluating negative 3 plus or minus the square root of 9 plus 8 all over 4 and this ends up being negative 3 plus or minus the square root of 17 all over 4. Just evaluating this answer, getting rid of the square root, I get x-intercepts at about 0.28 or at negative 1.78. Now I think we have enough information to graph this. I'm going to skip what I said was my step 4 because I think I have a good idea of how this function is going to look without figuring out where the behavior is around these asymptotes. So let's see what this looks like. So we've got all our important information. Let's mark in what we know. We know we have a vertical asymptote at x equals negative 1, and we really should mark in our scale first. So we know we have a vertical asymptote at x equals negative 1, but there is an oblique asymptote at 2x plus 1. And let's just recall that's of the form y equals mx plus b. b is the y-intercept. So at positive 1 we have the y-intercept for this oblique asymptote, and then our function goes up 2 and over 1. Or our asymptote goes up 2 and over 1. It rises 2. And it can also go down 2 and to the left 1. And now I just need to indicate my key points. So I know I have a y-intercept at 0 and negative 1. I have x-intercepts at about 0.28. And at negative 1.78, about there. And remember how things behave around asymptotes. We get close to the asymptotes, but we never quite reach them. So I know I'm going to be getting close to negative 1, but I'm never going to reach it. I know I have to pass through my x-intercept, and I'm going to get close to the oblique asymptote. But I'm never going to reach it. I'm also going to get close to that asymptote at negative 1, pass through my y-intercept and my x-intercept, and continue on like that. Okay, that's my poorly drawn function. hard to do on the smartboard. Let's see if we can get a better idea of what this looks like, maybe using Google Graph. So there's Google Graph's version. You can see very clearly the vertical asymptote and the horizontal asymptote, or sorry, the oblique asymptote. Okay, it's very clear there. So it kind of looks like mine. Not as nice though. So in class tomorrow, we're going to look at one more type of special case for these functions. Thanks for watching.